Hello everyone, welcome to a new video, and in this video we are going to discuss about how to convert a non-differentiable max operator into a more differentiable form. That can such that the gradient based algorithm don't get stuck this. So we are always discussing about from the point of view of wireless communication. So in wireless communication system, suppose we are maximizing the capacity of a system, capacity of a user. So the capacity equation, as we know, can be written as max of log to 1 plus gamma k. We know that. So here gamma ek is the signal to noise ratio. Okay, now this max of log to 1 plus gamma ek, this is the objective function. So whenever we this objective function, we need to, the gradient based algorithm will we need to find the gradient of this whole objective function. To maximize this complete objective, we need to find the gradient of this objective function. Whenever we are finding the gradient of this objective function, so here suppose our function is f. Here see, this is our function f. Now if we take a maximum of any f, suppose let us take it as like here f equal to, we need to find out the max of x comma minus x. Here x is suppose our f. Okay, anyway we need to find the maximum, and the max of x comma x is equal to, in mathematics, can be written as mod x function. Now graphically if we see, the mod x function is represented in this way, like in the right hand side of from the 0, in the positive side there is a positive slope, and in the left hand side there is a negative slope. This is for only mod x, max operator of the mod x function. So here if we take the gradient f dash of 0, that is minus 1, and f dash of 0 in the positive side, that is plus 1. So that means in the corner point at 0 point, the gradient doesn't exist. So our algorithm, whenever it is going to find the gradient of this kind of function, then it will get stuck in all the corner point like this. So our aim is actually that can we convert this max function into some more differentiable form, so that the gradient based algorithm doesn't get stuck. So can we do that? So one approach is, sorry for making the screen up, one approach is using log sum exponential, that is only called the log sum exponential. So I will first give the general formula, and then I will apply that log sum exponential formula in our this capacity equation. So suppose the log sum equation is called as, suppose we have to find LSE of A1 A2, we will prove that LSE of A1 A2 is equal to max of A1 A2. So LSE of A1 A2 can be represented as E log of exponential of A1 by U plus exponential of A2 by U. We will prove it. Okay, suppose in the first case A1 is greater than A2. Suppose if A1 is greater than A2, then E of A1 by U will be obviously greater than E of A2 by U. Then this E of A1 by U plus E of A2 by U can be written as E of A1 by U only. So U log E of A1 by U plus E of A2 by U can be written as similar as U log of E of A1 by U. E log of E of A1 by U, log and exponential will get cancelled, so it will be U into A1 by U to ultimately A1. So that is the similar as max of A1 comma A2 is equal to A1. As we have considered A1 as greater than A2, then putting this condition in the LSE of A1 comma A2 gave similar as max of A1 comma A2 equal to A1, right? So same thing in case 2 also, if we consider A2 is greater than A1, if we put that in the formula U log of E A1 by U plus E A2 by U, can be written as u log of e a2 by u equal to a2 only. That is similar as max of a1 comma a2. Now let's look for the case of when a1 equal to a2 equal to a. Then we can write as u log of e of a1 by u less e of a1 by u equal to u log of 2 times of e a1 by u, obviously. So this we will apply log inside this function now. Then it will be u log of log 2 plus a by u. So u log 2 plus u into a by u will be left by a. So whenever our a1 is equal to a2, we will get a max of a comma a would have been a, will be a. But when we put LSE of a comma a, then we are getting a plus u log 2. So there is a error of u log 2. But that is like boundary cross error, right? That much error, and whenever our u is small, then that error will be small. So what we can do from this, we learn that we can approximately put the log sum exponential function in place of max operator, and our gradient based method can use these things so that it doesn't get stuck. So now we will apply. This was our original rate formula, log 2 of 1 plus gamma ek, max of this we can write it as u LSE or log 2 of exponential of the entire thing, log 2 of 1 plus gamma ek by u LSE. LSE is the log sum exponential of the u, I have put it. Then by property, like this is, see, this we can break, one more step we can break this. So we know that e log of e to the power of x log 2y, we can break it as e x ln y by ln 2, right? So this thing we are trying to convert into a more manageable term, like e log 2 of 1 plus gamma ek by u LSE. We can write it as e of log of, only log of 1 plus gamma ek by u LSE into log 2. We can write this. It's just normal manipulation conversion, how so that we can convert it into a more form which can be handled properly. It get reduced to 1 plus gamma ek 1 by u LSE log 2. So we have successfully converted the max of log 2 1 plus gamma ek. That was our function or objective function that will go into the optimization algorithm, suppose. So the gradient based algorithm, whenever finding the gradient and whenever there is a corner point, it would have got stuck there because of the max operator, that we have successfully converted into a LSE form, that is a log sum exponential form. So I hope you have understood the idea of a simple idea of converting the max operator into a LSE. So that's all for today.